Hello, this is Math 2134 coming to you from the College Edu page, and this is the conclusion of the lecture entitled Limits. When last we left off, you were evaluating this limit. I gave you some time then. I'll give you some time now. Let's see how you did. You can't plug in h to be 0 because you will get 0 over 0, which is an indeterminate form. So what you're going to do in this case is multiply in a clever way by 1. So you're going to multiply top and bottom by the conjugate of this. We have the square root of 1 plus h minus 1, so we're multiplying top and bottom by the square root of 1 plus h plus 1 over the square root of 1 plus h plus 1. That's multiplying by 1, and then we have a minus b times a plus b. And so that's going to give us a squared, which is 1 plus h, minus b squared, which is 1. And so the ones will cancel, and we'll have h over h times this expression, the square root of 1 plus h plus 1. The h's we will cancel, and we'll have this. So this limit is equal to this limit, and now we can plug in h equals 0, and we get this as our answer, 1/2. Notice that we created the common factor of h that we canceled. Up to now, we've studied the limit of the function x as it approaches a finite number. There are occasions, however, when we want to know whether f of x approaches a unique number as x increases without bound, or decreases without bound for that matter. So consider, for example, the function p, giving the number of fruit flies in a container under controlled laboratory conditions as a function of time. So what happens is they multiply and they're growing, but then they start being constrained by their environment, and there is a limit here, and the limit is called the carrying capacity of the environment, and it's determined by the amount of living space and food available, as well as other environmental factors. This S-curve is a very famous curve, and we'll discuss that more later. Let's look at another example. This time, suppose we're giving a function y is equal to f of x is equal to 2x squared over 1 plus x squared, and we want to determine what happens to f of x as x gets larger and larger. You know what to do. Let's see how you did. Well, here's the graph of the function. You see there is a horizontal asymptote at y equal 2. So as x gets bigger and bigger and bigger, y gets closer and closer to 2. With that as motivation, let's talk about the definition of a limit of the function at infinity. The function f has a limit L as x increases without bound, or as x approaches infinity, and it's written this way. If f can be made arbitrarily close to L by taking x large enough. Similarly, the function f of x has a limit m as x decreases without bound. That means it approaches minus infinity. It's written this way. If f of x can be made arbitrarily close to m by taking x to be negative and sufficiently large in absolute value. So here's another example. We're looking at functions f and g. Here's f, and here's g, and we're to evaluate these limits for each of them. You know what to do. Let's see how you did. Here's a picture of f, and you see it's a step function. It is 1 if we're greater than or equal to 0, and it is minus 1 if we are strictly less than 0. And so what happens as x goes to infinity? It stays 1. As x goes to minus infinity, it is minus 1. Here, as x goes to infinity, this gets closer and closer to the horizontal asymptote of 0. This one gets closer and closer to the horizontal asymptote of 0. So what happens is those are the limits that we have. All the properties of limits that we listed earlier in the theorem are valid. when a is replaced by infinity or minus infinity. And additionally, we have this. If n is bigger than 0, so we have x in the denominator, and x is going to infinity, 1 over something that's getting larger and larger and larger approaches 0, and also, as it approaches minus infinity, 1 over something that gets larger and larger and larger in absolute value approaches 0, provided that this is defined. We often use the following technique to evaluate a limit at infinity of a rational function. Divide the numerator and denominator of the expression by x to the n, where n is the highest power present in the denominator of that expression. Let's use that to evaluate this expression. The limit is x tends to infinity of x squared minus x plus 3 over 2x cubed plus 1. You know what to do. Let's see how you did. So you divide top and bottom by x cubed. And so when we divide in the top by x cubed, we get this expression. When you divide the bottom by x cubed, we get this expression. Now the limit of the quotient is the quotient of the limits. And so I really will be using the theorem 2 to say that this becomes 0, this becomes 0, this becomes 0. So it's 0 over 2, which is 0. Here's another one for you to give a go. This is the f of x. We're taking the limit as x goes to infinity, and we're saying if the limit exists. You know what to do. Let's see how you did. In this case, we're going to divide all the way through by x squared in the numerator and x squared in the denominator via our special hint. And so we're going to get 3. This is going to go to 0, and this is going to go to 0. So the numerator gets to go to 3. The denominator, this will go to 0, and this will go to 0. So the answer is going to be 3 over 2. Here's another example, and you're supposed to evaluate the limit as x goes to infinity of f of x, and the limit as x goes to minus infinity of f of x. And here is f of x. You know what to do. Let's see how you did. So here, when you divide top and bottom by x squared, you get 2x. This is minus 3 plus 1 over x squared, and down here you get 1. And this is 1 over 2x, and so those are going to go to 0, and this one is going to go to 0. So you see, this is going to go like x. So as x goes to infinity, this is going to be growing like 2x minus 3, and that's going to go to infinity, and you have 1 in the denominator. So the answer to that one is infinity. Now, if we divide just like we did, but now we say x is going to minus infinity, well, 2x minus 3 is going to go to minus infinity, so this answer is going to go and be minus infinity. Life is a word problem, and so we have word problems. Now here we're introducing the idea of an average cost function. So here's the total cost function that we have, but we want to know the average cost, so you see c of x is the total cost of making x units, but if we divide that by x units, that is the average cost. We call this average cost c bar. So c bar is c of x over x. That's the definition you want to remember from your business, for your business training. So we're going to take c of x divided by x. We're going to divide x in, and we get this expression. So what, as we take the limit as x goes to infinity, what will happen is that this part will go to 0, and this will end up being 100. I really didn't let you work on that, but I should have. Here is what I do, and the answer is 100. Notice that that's going to be the asymptote, again, a horizontal asymptote. Last but not least, some of you who've studied trigonometry remember that there are things that are the sine function that looks like this, but this is just really going up and down and up and down and up and down, and it does that forever. It asks us to explain why the limits don't exist, either going to positive or minus infinity, and that is they never get close to and stay close to a number. They go up to 1, and then they go down to -1, and keep doing that. So they never get close to and stay close to a number. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.